Okay, so welcome back. Today we'll be looking at methods for solving systems of linear equations. For those of you who have been at NTNU forever, it's Modification all over again, at least in the start. So we were looking of problems. Well, we were looking at problems of the type A x equals b, where A is a real n by n matrix, and x b are real vectors, or real valued vectors. One. So what's a system of linear equations? Well, an easy one is, for instance, x2 plus 3, well, with x1, 2 equals 4, and x1 plus 2 equals 1. So that's a very simple system of linear equations. So in this case, A is just the coefficients on this side, so it's going to be 1, 3, minus 1, 1. X vector is the unknowns, which, the x1, x2, and the b vector is the right-hand side, or 1. We can then write this on that form. That's going to be just 1, 3, minus 1, 1, x1, x2 equals 1. I do hope that's known beforehand. Yes, good. This is a very simple example. So, how do we know that we can actually solve this system? Well, we can check the determinant. So if the determinant is not 0, then we can actually solve this. But how do we solve it? We solve it by something called Gaussian elimination, which is matrix operations. So I'll just quickly go through this, because it will be, hopefully it's known. The thing is that you run into some problems when you're trying to do Gaussian elimination numerically, which I'll show an example of. So, Gaussian elimination. So, what are the operations we can do? Well, we can interchange rows. Basically, we can change these rows and it will be perfectly fine. It's the same system. We can scale them. Meaning that we just multiply this equation, or this equation, by some kind of number. Just scaling it, basically. Or replacement. So replacing an equation, for instance this, by the sum of itself on a non-zero multiple of something else. So that's basically taking, for instance, this and adding it to this to solve this out. Then you have done Gaussian elimination of the system. So numerically, we would like to have the form on an upper triangle. Numerically, we would like to have the matrix on an upper triangle form. Basically, when we do Gaussian elimination here, see if we have one of these down here, then we will get 1, 3, 0, 4. And then we have an upper triangle form. That's what we want in numerical Gaussian elimination. What we're doing here is called pivoting. So, well, we use row as kind of the base. To eliminate the rest of the column. So this works well and good on paper, but in numerics, we need to make sure that the pivots are of the same order, or else we will get into trouble. Same order of magnitude. So why do we need to make sure this actually happens? Well, round of error. Yeah. Same order of magnitude. A kind of line standing in front of the blackboard. Okay, so an example why this is important to make sure. So, we'll be looking at the 0.3, 0, 0, x1 plus 59.2 equals 0.17, 5, 1, 0, it's 1 minus 0.2 bit of skipped some zeros there, but 46, 78. So in mind, we'll see that the true solution of this system is 10.0 and so this is the true solution. Now we'll see if we just do the Gaussian elimination and not thinking about the order of magnitude, we'll get the wrong answer. Completely wrong answer. So the exact or true solution is true. Okay, so how would we do this numerically? Well, we have to figure out, so if there's solve 5.1 or 3 6 repeating, and this is where we do the error. Do an approximation. 7, 4. So we need approximately, so write this matrix form, 3, 5.91, 5, 13, and in order to do Gaussian elimination here, we need approximately 1,774 times this equation and subtract it from this one. Yep. So what will the solution be? Well, yep. Do this, we'll get the matrix 3, 5, 9, 4. Then we will get big number, so 0, because that's what we're doing. We're eliminating this. Here we'll get minus. What's this? 104,300. Approximately 7, 4, 400. Okay, so if we then try to solve this, so this is just numbers. I'm giving some details. If you want, you can do this by yourself, I hope. So solving this, we get that, so x2, this should be easy. x2 is approximately, well, I can do it like this. Minus 1, 4, 0, 5, 5, 0, 400, which is the same as 1.001. Okay, that's not too bad, is it? That's fine, but for x1, we get 0.17 minus 5 0.01, 3. Yeah. Where? This one? Because we also need to do this with the b vector. Yeah, the vector. So we have this number times 1,764. We have 46.78 minus 59.17 times 1764. So that's going to be approximately this number. 10. Ah, yes. This. No. No, it's not the same number. It's so yeah, we take this row beneath that. So if you look at the augmented matrix, maybe that's better. Then it's going to be this number 59.17 4 6 7 8. Then you do the minus 1 7 4 this. That's why you get these large numbers. Both of them? No, just for this row. This is just regular Gaussian elimination. Yeah, but yes. So you multiply this system of equations by this, and then you add it to this to eliminate this number. So you're using this as a pivot. And this number is a pivot, and that's not of the same order of this. Okay? So this is where we get errors. So have anyone tried to calculate this? Okay. This is approximately minus 10. So x2, this, suppose the true solution is 1. Okay, not too bad. But for x1, we get negative 10. The true solution is 10. That's bad. Okay. So that's because we've not adhered to this rule. We need to make sure that the pivot's are of the same order of magnitude. Is this? Okay, so what happens if we do it the other way around? If we actually switch these rows, then we will actually get the correct solution. So yeah. So we need to change rows, or we need to make sure that the largest number is used as a pivot. Yes, then it will work. I mean, if you do this exactly, then I mean it would work. It would still work, but we're doing an approximation here, up here. That's why it's not working anymore. So the approximation here is devastating. So how to solve this? We need to of equations before we perform Gaussian elimination. So in this case, it would just be to interchange the rows. So if we try to solve the system 5.28, three rows, 3, 9, 14, 4, 6, 7, 8, 9.17. Then it will work. We want the largest coefficients along the diagonal. So it's still the same system of equations. You can do homework to actually solve this if you want, and then see that that works. And that's sometimes called partial pivoting. So, how do we do partial pivoting? 1. Other values, column P on or below the diagonal. Next, we find the row K with the largest value. And then we exchange rows P and Q. Rows P and K if K is larger than P. It depends. I mean, it depends on the system. So all volumes in column P. So if we're now looking at this, we're looking at all of the column. No, let's see. I can actually use this. So we're looking at all the values in this column P here, and then we're finding the largest ones. And if one of the values below this P here is larger, we exchange them. So that, yes, in this case it's correct. You don't have to do anything. And this is just a 2x2 system. I mean, we can also do it here, but then you already done the Gaussian elimination step, and you have it on an upper triangle form, and you're done. So then you're finished. But if you have a larger system, then you first have to do the first column, then P is 1, and then you've done this one, then P is 2, then 3, and then so on for larger systems. But partial pivoting might not always work. So then we have something called a scaled pivot. This is a modification of partial pivoting. One. Now we're going to first search through the row. So row P or P to N, I guess. P to N. After the largest absolute element. So I'm going to abbreviate element with ELT. Because I'm lazy. Again, we're working on the rows. I'm going to call this number as R is maximum of A R P R P plus 1, so on. Well, A R N. Where R is P plus 1 N. ARP. Yeah. So yeah, these subscripts. That's the position of each element. So regular matrix A11, A12, A12, and so on. A1, N. Get down here. A and 1. And A and that's what the subscript means. So you're just basically looking for the largest element in each row first. So first, if I'm in the first, trying to look for the first column, here I'm just looking through all of these down here, and then S1 will be the largest absolute valued element in this row, S2 in the next row, Sn will be the largest valued element in this row. Largest absolute valued element. Okay, and we found those. Then the pivot element on row K selected. E, E, K, and the maximum value of all of these. P, P, so we're basically just scaling all the rows with the largest element in that row. Okay. So in words, more of a verbose form. So that is search through elements, column E, that are on or below, diagonal, after the element that is largest relative to other elements. Own row. Okay. So you're basically just scaling each row with the largest element in that row, such that the largest element in each row will be basically 1, because the largest divided by the largest is 1. The rest will be, well, an absolute value will be less than 1, or actually 1. But oops, we have other tricks to try to directly solve. That is LU factorization. Want to factor a matrix A into its lower part and its upper part, such that multiply these matrices, we get A back. Then we can just do forward and back substitution. I'll start with that. So, yeah. So matrix factoring. So every non-singular matrix A has a triangular factorization. So non-singular means that you can actually solve the system. The determinant is not 0. For factorization, A equals LU. Okay, so what does this mean? Well, first, singular, this means that determinant of A not 0. Want is A element form 1, 1, A1, N, 1, N. Should be written form 1, then just zeros, L to 1, L, and 1, L, oh, this is 1 also. 1. So along the diagonal on the lower triangular, so it's going to be 0. Ones, and then we have some numbers here. The rest of the elements are going to be 0. U, U1, U1, N, U, N, diagonal here, 0, like so. This is A, L, U. Okay, how does that help us? Try to do some math. Yes? It doesn't have to, but most probably it will. I'll get to that. It's basically how you solve it. Then we'll see that, well, in most cases, there will just be 1 along the diagonal. Yeah, U is not 1. So, I'm going to assume that we can write A on this form. U solve equals B. That solving LU is X equals B. And X. So first, we're trying to solve for y. So this is just something we introduced to make it easier. That means we want to solve first y equals e. I mean, we have u, only x is unknown, but just means we're scaling all the vectors. Solve this by forward substitution. So why can we do this? Well, we know that the first element, so L, is lower triangular. So we know that this element has to be, or the y1 going to be the first element of B. Yeah. So now we have we have determined one of the unknowns. Okay. Then we go to the next. Then we only have two unknowns, where one of them is known. So we just substitute it in, and then we solve this equation, and then you substitute going downwards. This. Okay, so this is basically just notation to make it easier to kind of keep in your head. So AX equals B, okay? We assume that A can be written as LU. So that's basically just inserting. So LUX. And then we are introducing this Y as a scaled X vector. Okay, so it's just some new Ys. So we can solve this problem. Okay, so now we can solve this by forward substitution. And then we have the next problem. So now we have solve this one for the y's, because now we are finding the y's. So now we know this, and we can do backward substitution down here. Yes, it should be a vector. Oops, and also solve has an E in it. Okay, so when we have A equals LU, then it's easy to solve stuff. The problem is actually finding LU, which we will do after the break. Less questions?